Let's take a look at an example for Module 8.1 for ME12 Dynamics. So in this problem here, we have a fan. They tell us we have an omega here. They give us our radius down here at the motor. They give us the radius of the inner hub here, and they give us our radius of the fan blade here out to point P. So in the problem statement, they tell us that the some motor M begins rotating with an omega given to us by this relationship here, 4 times 1 minus e to the negative t in radians per second, where t is given to us in seconds, and the radii of the motor, fan pulleys, and fan blades are 1 inch, 4 inch, and 16 inch respectively as shown in our diagram. Now they want us to find the magnitudes of the velocity and acceleration at the point P on the fan blade when the time is equal to 0.5 seconds. So our plan of attack to solve this problem, first step, we're going to determine the angular velocity and acceleration of the motor using our kinematic relationships of angular motion. 2, we're going to assume the belt does not slip, and that the angular velocity and acceleration of the fan are related to the motor's values by the belt. And third, we're going to say that the magnitudes of the velocities, acceleration, and point P can be determined from the scalar equations of motion for a point on a rotating body. So now that we've had a chance to read through the problem statement, understand what they've given us in the wording and the initial diagrams, and what they're asking us to solve for, our next step is to create our setup page here. So for this example, I redraw out my diagram. Here's my motor M down here. My R sub M is 1 inch, my R sub P is 4 inches, and my R sub B for the blade is 16 inches here. There's my omega. So my omega is given to me in the problem statement as 4 times 1 minus e to the negative t in radians per second. My R sub M is 1 inch, my R sub P is 4 inches, and my R sub B is 16 inches, and they know that my time is 0.5 seconds. I'm looking for the magnitudes for velocity and acceleration at point P on the fan blade when my time is equal to a half a second. So now I can begin my solution here for 1 for my plan of attack. Since the angular velocity is given as a function of time, by this relationship here, my omega m is equal to 4 times 1 minus e to the negative t. The angular acceleration can be found by differentiation. So we'll take d over dt of our omega sub m in order to get our alpha sub m here. So we take the first time derivative of our omega sub m, d over dt of our omega sub m right here. What we end up with when we do that out is 4 e to the negative t in units of radians per second squared. Well, we know that our time is equal to a half second, so we can plug in our time to both our omega m and our alpha sub m here. So we plug that in for our time value here of half a second. So we end up with omega m is equal to 4 times 1 minus e to the negative 1/2, or 1.5739 radians per second for my omega m. And my alpha m is 4 times e to the negative 1/2, or alpha m is equal to 2.4261 radians per second squared. So going on to step 2 of our plan for our solution here. So since the belt does not slip and it does not stretch, it must have the same speed and tangential component of acceleration at all points. Therefore, the pulleys must have the same speed and tangential acceleration at their contact points with the belt. So from that, we know that the angular velocities of the motor are omega sub m, and for our omega sub f for the fan are related by the following relationship here. Velocity is equal to omega r. So for our case here, our omega m, omega r for the motor, and our omega f and rf for our fan. So we can plug in our known values here. We have our omega sub m. We just solved for that by plugging in our known time of 1/2 second is equal to 1.5739 times our radius of the motor is given to us as 1 inch. This is equal to our omega f for the fan times our radius for the fan that we already have in our given problem statement. Our only unknown here is our omega sub f. So we can solve this equation and rearrange our omega sub f is equal to 0.3935 radians per second. So continuing on to part 3 of our solution here, we see that the tangential accelerations are related by the following relationship, just like we did our omegas here, by this here, that A is equal to alpha r, so A sub t is equal to alpha m times Rm for the motor and alpha F times Rf for the fan here, where we know our alpha M, what we solve for based on our t is equal to a half second of 2.4261, radius of the motor is still the same, 1 inch, is equal to our alpha F, which we're going to solve for, and our known radius of F here, which is 4 inches. Only unknown again now here is our alpha F. Solve for this, our alpha F is equal to 0.6065 radians per second squared. So the fourth part of our solution, now the speed of point P on the fan at the radius of 16 inches now can be determined by the following here. V is equal to omega R, or V sub P is equal to omega F times our R sub P here at that point there. So we can plug in, because our omegas are going to be the same there. Those are connected rigidly. So V sub P is equal to that omega 0.3935 times that radius of 16 inches. So V sub P, when we back that out as our only unknown, is 6.3 inches per second. So from here, the normal and tangential components of acceleration at point P can be then calculated. So our A sub n and our A sub t are calculated based off our formulas here. A sub n is equal to omega squared r, and A sub t is equal to alpha r. So if we start with our A sub n is equal to omega f squared times r sub p for the corresponding components here, plug in our known values. Our omega sub f we know as 0.3935. Take that quantity squared times r sub p, which is 16. So therefore, our normal component of our acceleration at that point P on the blade is 2.477 units of inches per second squared. Our A sub t is alpha f times our rp. Plug in our known values. Our alpha f is 0.6065 that we just calculated, times our r sub p is 16. Plugging those in, our A sub t is 9.704 inches per second squared. Now this asks for the magnitude of the acceleration. So the magnitude here at point P can be determined by the square root of the sum of the squares of the individual components. So we do that there. A sub n squared plus A sub t squared times the square root. Plug in our known values. A sub n is 2.477. A sub t we just found to be 9.704. Square both of those, sum them together, take the square root. A sub p is equal to 10 inches per second.